Okay, so here we are. I'm going to do the second example of contact stress for class 8. We have a pair of mating steel spur gears, right? So they're both steel with a 0.75 inch face width that transmit load of 40 pounds. For estimating the contact stresses, make the simplifying assumption that the teeth profiles can be treated as cylinders, I guess, with instantaneous radius at the contact point of interest of 0.447 inches for what's often, for one of them to be the pinion, and I think for the gear, it'll be 0.62 inches. And estimate the maximum contact pressure, the maximum shear stress experienced by either gear. And they didn't ask us for the location for the thing underneath the surface, but they totally could have. Right. So here we go. Let's work through this and write down some things we want to know. The elastic modulus of this one is 30E6 psi. And the Poisson's ratio, I'm going to use 0.29. That's what I have down for my values in what I have written down. So that's what I'm going to stick with. I probably should fix it and make it 0.292 to correspond with the book. If you'll recall, I said that in table A5 right here, we have an elastic modulus, according to them, for carbon steel of 30 and a Poisson's ratio of 0.292, right? And by the way, this is what I'm used to, and I use this quite often, but for many different textbooks or sources, well, it'd be more like 29 or even 28.5 for many different kinds of steels. But we don't have a whole lot of variety of different steels right here. This is the information we have available, so we're going to often just go ahead and use those. For some reason, I used 0.29. I don't remember why. And oh, by the way, the graph is that we base everything on in terms of stresses are 0.3. So there you go. So they're saying the face width, that for a gear means this width right there. So that's what they mean by the 0.75. I just thought I'd point that out, 0.75. So that's L when it comes to a cylinder is 0.75 inches. The force they're telling us is going to be 40 pounds, which is pretty small, but it's okay. 40 pounds taking place. They have a radius of curvature, right? So they're saying that the radius, so they're saying this radius, this curvature right here is like has a instantaneous radius of curvature. For one of the gears of 0.47 and the other is 0.62. We need diameters in our equation. So let's say we will write down R1 is 0.47 inches. Therefore, D1 is 0.94 inches. And then R2 is equal to 0.62 inches, and D2 is equal to 1.24 inches. And now the next thing I want to do, I'm going to figure out the half width of how much deformation is going to take place in the cylinder, right? In the two cylinders. So we have this right here. So this is what we're going to look for. We're going to go for that right there. We're going to calculate B, which is up here, B, right? So we want this equation right there. And so I'll write it out. It's not that long. B, way over here to the left, is going to be 2 square root, not cube root, 2f pi over L. And then 1 minus nu, this is the same material, so I'm not going to have to do that. I just have to do it 2 times. 2 times 1 minus nu squared divided by E1, right? So we didn't have to write it out. And then this is over 1 over D1 plus 1 over D2. Sticking some numbers into this. We have 2 times 40 for our F, divided by pi, divided by 0.75. 2 times our 1 minus, and I used 0.29 squared, and I probably should have used 0.292, and there's 30E6 right there, and then we divide this, is going to be 1 divided by 0.94 plus 1 divided by 1.24. So we're going to get a B, small number, of 1.0528 E minus 3 inches is the half width of that flattened area in the cylinders. So we get the P max, and that's going to be 2 times F divided by pi BL, right? That we found right there. Don't need any of these equations. We're going to need this here in a second. We don't really need it actually, but that's okay. 2 times 40 divided by pi and 1.0528 E minus 3 and a 0.75, and we get a P max of 32.25 KSI. I went ahead and made it into KSI, right? So I divided this by 1,000 and then wrote it down because I'm lazy. And then estimate that's the estimated contact pressure, maximum contact pressure. And now the maximum shear is simply, based on this right here, is going to be 0.3 times that value right there. So that's really kind of pretty boring right there. Out, we get the tau max is equal to 0.3 times 32.25, so we get 9.68 KSI. It's a simple. These are simple problems. Just trying to see if you. I don't know what we're trying to see, but they're trying to. When you ask the problem and students aren't familiar with it, and then they start going into the book without actually reading it, and then they start looking for equations and they start plugging things in and getting all frustrated. But if you read the caption or you read the content or have listened to me in class, you'll know that's just a pretty simple, straightforward problem where we're just calculating some numbers. And it really doesn't mean a whole lot until you start comparing it to the strengths of stuff. So I'm going to do some more examples now in separate videos of that are review of what we have covered so far this semester, in up to class 8, and so stuff in chapter 3 and the review that you'll need. So we'll talk soon again.